My name is Jochen Steierwald and have been working with Electrobit since 2011 in various roles and mainly in the area of service projects and also lately focusing on the product trainings on the EB tresos and EB Corpus product lines. So these are the two product lines for our implementation of the AUTOSAR standard. First of all, let's have a look at the agenda. Today I will start with a brief look at the evolution of the AUTOSAR standard to bring everybody on the same page, then go to the EB specific implementation of the AUTOSAR Classic platform. Next, we will have a look at the tooling aspect of the AUTOSAR methodology and especially on the scope of EB tresos Studio in this context. And finally, I will show you a typical configuration and integration workflow, and I will do this not only based on some slides, but also directly using the tool itself. Yes, the evolution of the AUTOSAR standard. Let's recall that the AUTOSAR standard has quite a history, now 17 years since it was founded. First usage in serious production was starting with release 2 in 2006. And I would say it's the established default platform for most OEMs since release 4, which was back in 2009. Since then, the focus is on adding features based on the increasing requirements, especially in the area of multi-core, Ethernet communication, and lately cryptography, security, and in general, and multi-core distribution. Because multi-core support is not only needed for the application, but also for the basic software, and that now in the latest release includes even the microcontroller abstraction layer. So this is basically the very brief history of the AUTOSAR Classic platform standard. And now let's also have a look at the main working areas. There are basically 4 areas. The architecture, which is the fundament of the AUTOSAR standard, but the methodology has also always been a key or major key for the overall AUTOSAR concept. And my presentation is focusing on this part, the methodology. So let's have a closer look at the definition of the methodology. It defines an exchange format, or actually the exchange formats, and also a description template to enable a seamless configuration process of the basic software stack. Exchange format means that everybody who's using the AUTOSAR methodology has to speak the same language, and this is an XML format defined by AUTOSAR. That is one part. And of course, the description templates also had to be specified regarding its content, not only regarding its structure and syntax. And this is a bunch of specification documents in AUTOSAR referred to as templates. And it includes even the methodology how to use this framework. So it is already defined by AUTOSAR, but what the methodology does not define is the tooling itself. So it's quite similar to the implementation of the basic software up to the open market, and different software and tool companies compete here on the market, and they will provide their own tooling, which of course has its main objective in supporting the AUTOSAR methodology. On this picture, you see the areas of the EB tresos product portfolio, which implements the classic AUTOSAR platform. Starting with the basic software, here the product name is called EB tresos AutoCore, and it's an implementation of the AUTOSAR compliant basic software for automotive ECUs. The operating system next to it is here a separate product due to its hardware dependency. The second part is the tooling, and we call this EB tresos Studio. It's the ECU basic software configuration and integration tool in one single environment. That means it is suitable to take care of the complete basic software stack configuration, even if some of the modules are not developed by EB but by third parties. This is often the case for the microcontroller abstraction layer. Now, when it comes to the tooling aspect of the AUTOSAR methodology, it's worth to have a look at the big picture, showing the different steps which are covered by the methodology. Starting on the left side, a system, so in our case, a car is defined, which contains a description of the software components, resources, and constraints, and so on. Certain decisions also will be taken here, such as the mapping of software components to the ECUs at some point. This work is usually in the responsibility of the OEM who develops the car, and the tooling used to do so is referred to as an AUTOSAR authoring tool. At some point, the transition from the overall system to the specific ECU, which implements a part of the system, will take place. This is when we arrive to the right side of this picture. And here, the tooling aspect of the ECU side is on taking decisions which are only relevant for this specific ECU and the configuration and integration of the complete basic software stack. So enable it that it will provide the desired functionality for this ECU. This is in the scope of the integrator, and the work is usually in the responsibility of the tier 1 who implements this specific ECU. Regarding the naming, AUTOSAR here refers to as a generic configuration editor. And just to complete, also in a final step, the code needs to be, or the configuration needs to be translated into compilable code to finally achieve the executable. The EB implementation of the tooling is in this part here, the EB tresos Studio, and this is also what my presentation will focus on. Also, the next few shows how the scope of EB tresos Studio is defined. This is a similar picture, but a bit differently explained. So we have here the system on the top, taking out one ECU, and finally in the ECU, EB tresos Studio is handling the configuration of the ECU basic software. You also see which are the exchange formats used. So besides the EPC files here, which are actually also technically AUTOSAR XML files, tresos is using an own file format for storing the ECU configuration, which allows for embedding additional features like describing constraints between configuration parameters. So this is why here the XDM format appears as an additional file format. Okay, so having talked about the scope of tresos Studio, now let's have a look at a typical configuration and integration workflow. And we will look at an overview of the internal data handling in EB tresos Studio, which will help to understand the different steps that are required in the workflow. So just like in the methodology, also the tooling has a system side here on the left side and an ECU side on the right. So this is also represented in the tooling. The system side is mainly filled by importing the relevant parts of the system description, and EB tresos Studio itself can only selectively modify this data. The import is illustrated here. EB tresos Studio has a bunch of different importers, mainly, of course, the AUTOSAR system description language is supported here, but due to some projects still using legacy files like DBC files, FileX files, the legacy files can also be imported here. All of this ends up in the EB tresos internal system model. At the end, this is a database file, and the selective modification I was mentioning is here below, though it's possible to establish connections between unconnected ports, and also the system signals can be mapped in tresos Studio. Apart from that, the complete system model relies on the files which are imported into tresos. The bridge to the ECU configuration side on the right is done by using the import ECU config wizard, which allows to derive directly from the system description certain parts of the ECU configuration. And the second part here plays the RTE editor, which brings together the scheduling and communication needs of the application with the respective services provided by the basic software. So when we now go through the workflow, we will also highlight here the relevant parts that you also understand how this relates to the internal behavior of the tool. Let's start with the first step of the workflow. Here, I will import the system description to tresos Studio. The main content are the topology, but also the communication matrix, software component to ECU mapping, but also supplementary descriptions like the definition of data types will have to be imported here. I will now switch to the application to show you this workflow step 1. So I have prepared here a project, which I will now open, consisting of a bunch of basic software modules. You see just from the number of modules that this is a very stripped down basic software stack, only using some elementary modules, which we will have to use here as a base. And the import to this project works here in the way that I use the importer dialog, and I have already prepared such a system description importer, and the importer itself can also be configured. The main configuration of the importer is to define which files shall be imported. So I have here prepared a folder that contains all the files which make up the system description in my example. It's not just one file, but you see a bunch of files, in total 5 different files. So the system description can, of course, be distributed to several files. This is a typical use case. And my dialog here allows me also to use wildcards. So in this case, I do not have to provide all the file names one by one, but I can provide here a wildcard filter that allows me to include all the files, or let's say at least all the XML files which are contained in this folder. For example, here we have some file that contains a topology, some file that contains a modeling of software components. Also service interfaces are defined here since they are referred to from the other description folders. And finally, a top-level composition, also a mandatory element of the system description. When I finally execute this importer, I will only get a feedback from tresos Studio whether this has been done successfully or not, including a list of errors and warnings if they apply. In this case, I have 3 warnings. Later, I will talk about how to get rid of these warnings, but at the moment, I will just close this dialog and show you the result in tresos Studio. For that purpose, tresos supports the system model viewer. It can be found here in the sidebar, and it will open here a view where I can see just what I have imported now. Even though tresos is not the tool to modify the system description, it's important that it allows to look at what is currently used by tresos as a system model. And here you see the tree view on the packages, like they are called in the AUTOSAR definition language. And I see, for example, here in the counter demo package, a couple of software components, mainly here, so-called software component cyclic counter, which is an example software component also used in our trainings. But also the system, including here the defined communication matrix and the networks, the topology, all of this is also now imported to Tresos Studio and therefore known to the tool. So that's the first step in the process of importing a system description. Let's move on to the second step. It's called complement system description. And in order to explain you what I mean here and why this is necessary, let's have a look at this picture. In fact, not only the application, but also the basic software contributes to the system description. Because the basic software may also provide sender-receiver or client-server ports and also the internal behavior, like the scheduling, and all of this will be described quite similar, like it is done here for the application part in the software component description, also for the basic software. So the basic software description is part actually of the system description, with the main difference that we need tresos Studio to generate it, because the description is even depending on the actual configuration of the basic software. So it's not a static description, but a description that also needs to be provided by Tresos Studio. Right now, when I imported, this kind of description was not part of the import, and therefore it is also not known in the project for Tresos Studio. So in the second step now, I will move on and complement this. And the way to do so are two steps. So the first step is to trigger the generation of exactly these basic software module descriptions. For that purpose, I go here to the build project, generate SWCD. And after doing this, I will get in the output generated SWCD folder a bunch of basic software module description files. In principle, you can say that each of my basic software modules that is part of my project also creates one of these basic software description files. Base is not an AUTOSAR basic software module, but Base is a plugin in Tresos Studio that, for example, is responsible to generate the base data types. And by adding this now to the Tresos system model, I will make sure that all the elements that refer to these type definitions of the data types will also be resolved. After generating this, I will modify the system description importer. I've already done this here. So you see that as a second entry here, I have added now exactly the folder that I was just showing, which contains the list of generated basic software module descriptions. And I still have my other files that I was importing previously here in this importer as well. And the reason is I want to make sure that the import always contains a complete set of files which are needed. This is because I will here override the existing model with the content of the selected files. This is a setting. Tresos allows here also to merge the files. In this case, I would not have to keep the first line here in my importer as part of the import, but it is recommended here not to use the merging, because merging is always a possible source of issues that come up with the merging algorithm. Therefore, if you add it like this, it is made sure that all the files which are imported are the only content of the resulting system model in Tresos. Again, I will run this importer, and afterwards checking the result in the system model view. As you can see here, in addition to the packages shown before, I have now a lot more. The first ones all refer to the description of the different basic software modules. So I have here a basic software module description of the DEM. In addition to these general descriptions, there are also corresponding descriptions that refer to the actual implementation. So the EBDEM implementation here adds a few more parts to the description, and they end up in a different package. So still my application here in the counter demo is part, but now in addition I have also all the basic software modules visible and part of the system model, and that is important because they need to be known, especially to the RTE editor, exactly in the same way like the application. There is another way to perform this step, and this is the update service component and BSWM descriptions wizard. But again, this wizard works with merging algorithm, and for big projects, therefore, it is recommended to use the way I have just presented. Let's move to the third step. And the third step is something you might not sound so logically on the first look, because it is called generate ECU extract. So you could ask, isn't that already done with the OVM, delivering the relevant parts of the system description to the tier 1? The answer is yes and no. And to understand the complete meaning of the ECU extract, it's worth to have a look at the system template. So the picture on the right side here is taken directly from the AUTOSAR system template specification. And here we see that the ECU extract is not just filtering out the software components which are mapped to a different ECU, but also a transformation from a hierarchy of software components into a flat representation, and a bunch of other measures, just like combining port connections, aggregating mappings, and so on. So all of this is in the AUTOSAR definition also an ECU extract. And this is usually not done by the OEM, so it has to be done also as part of the ECU integration process. The ECU extract serves as an input model for the RTE, so it's really mandatory to be used. And now we will have a look of how this looks like, but first let's have a look at the picture here, which I was just mentioning. Here we see software components belonging to different ECUs. So in the ECU extract, the non-relevant software components have been filtered out. But in addition, you see here, for example, that the port connection, which consists of 2 connections, or actually 3 connections, here a delegation connector, an assembly connector, and another delegation connector. All of this is now resolved to just one assembly connector. Just to give you an idea of what really happens here in the background. Again, we will perform this step directly in the tooling. For that purpose, I have created here the next step. And it's pretty simple because there is, again, a wizard available to take care of this. The wizard is called create ECU extract. And the first time I execute it, it will also ask me for which system and for which ECU instance the ECU extract should be created. Because depending on what was imported to tresos, the system model might now contain the description of several systems, or at least several ECU instances. In my case, the example shown, there are 2 ECU instances, and I want to create the ECU extract for the ECU test node. So I select this, run the wizard, and it tells me that it's done, and without errors and warnings, which is good. And now I will again check what happened internally to the tresos internal system model. By opening the system model viewer, looks pretty similar, but if you have a close look, you will see that there is one more package added to the system model. And not surprisingly, it is called ECU extract. And here we now have a flat map, and the flat map contains as a list of instances, basically all the entities in a flat representation, including the software components and the ports. So this is now very important because this is the input to the RTE editor. Now, before executing this step of the workflow, my RTE editor would not be able to see actually what is inside the system. I also will open the RTE editor at this step just to show you how the instances look here. I need to switch here to full first. Then I see in the implementation selection tab software component instances. In my case, there are just 2, and a list of basic software module instances. And all of this is known since I have generated basic software module descriptions and imported them to the system module. That was the third step. Now I will move on to the fourth step. In the fourth step, I will derive the ECU configuration from the system description. Background is here that major parts of the communication stack and also the diagnostic stack are already described in the system description, namely defined by the OEM. And configuring the communication stack and diagnostic stack manually would be a lot of work and very error-prone. So it's very important that the tooling supports a translation in the language like it was defined by the AUTOSAR system template into the ECU configuration. Of course, there's still a part which needs manual configuration that is still required to complete the ECU configuration. Just to mention a few things, for example, vendor-specific parameters, of course, will not be configured automatically by the system description. The assistant which will support this activity is called Create an ECU config. And I will show you this in the tool again. For that purpose, I will open the project which is prepared because now I have added a few more modules to my project to demonstrate this on the communication stack, in this case on the CAN stack. So you see that CAN interface, COM, but also the PD router are now modules added here into my project. And I want to configure them based on the information which was already imported as part of the system description import. Again, Wizard helps me to do so. And before I can use the Wizard, I need to configure it. So I go here to the unattended Wizard configuration window, which allows me here to select the Wizard. And I will configure now this to behave in the way that I want it to behave. Sorry, it was the wrong one. So here I see a list of modules which actually can be configured by using this Wizard. And as mentioned, these modules all belong to the communication stack. The default settings is that it will not configure the module, but of course I will change this now by selecting all of them. This way I make sure that the Wizard will take care for all of these modules. I can also run it directly from here. And after doing so, I see that a list of modules here has been colored in blue. That means that now the importer has done something here. And I will just go here to one of these modules to show you what actually has been imported. So there's a config set. And inside the config set, I see now a CAN controller. It's called ECU test node. And the little yellow overlay icon also indicates that this is not a manual configured parameter or container in this case, but it has been imported. As for the CAN hardware objects, I also see that the importer created here 2 CAN hardware objects, one receive, one transmit, and they are responsible for holding the data that shall be sent on the CAN bus. Of course, in a real project, this list would be much bigger, and therefore it is really important that the tooling really here takes care to derive this configuration items directly from the system description. And it's doing it throughout the stack. So also can interface COM, could also check here briefly how it looks like in the COM configuration, where we would expect to have here some PTUs configured that match to the configuration. You also see that there are still some configuration parameters which are not preset by this assistant, but they have to be either manually configured or by using other wizards, like in this case, the calculate handle ID wizard, which would then make sure that the handle IDs are calculated also throughout the stack. As I mentioned, the create ECU configuration wizard supports the communication stack, but since several AUTOSAR releases, it also supports the diagnostic stack, at least if the OEM provides here also a so-called diagnostic extract. Being done with the fourth step, let's move on to the next step. And unfortunately, not the complete stack can be derived from the system description. Therefore, all the other basic software modules, they need to be configured manually according to the ECU requirements. So this is just typical work that needs to be done, and I will not go into much detail here since the configuration of the complete basic software stack is way beyond the scope of a 1-hour webinar. But I will show a typical case that has to be performed by using the RTE editor, and it's about the mapping of events to tasks. So this is a decision which will never be predefined by the OEMs as part of the system model. It's a purely relevant issue for the specific ECU implementation, and therefore it needs to be done manually. Before I can actually map the events to the tasks, I need to make sure that the tasks exist. And for that purpose, I will go briefly here in the OS configuration editor. There are already some tasks for the basic software, but now for the application, I will just create 2 tasks. One for the timing triggered events. I have to give priority to this task, and a second task here to take care for the event triggered events of the application. And events should always be able to also interrupt the time triggered, and therefore I will give it a higher priority. That is just some preparation I will do before now doing the actual mapping inside the RTE editor. The RTE editor, by the way, here is an advanced editor because the configuration of the RTE is quite complex, and therefore we have a second graphical user interface that also supports an easier handling of the RTE configuration. The event mapping happens in this tab, and I see already here some warnings, and these warnings directly refer to that an event is not mapped to a task. So it tells us to perform the job that I now want to demonstrate. It also shows here a list of the unmapped events, and all of them belong to my application that I have imported. 3 of them belong to the software component cyclic counter, and 1 to the IO hardware abstraction. You also see the event types. So I have 2 timing events, and I will now map these 2 timing events to the RTE time task. And the other 2 I will map to the RTE event task. So it's pretty simple here to perform the mapping. And at the end, when the list here of unmapped RTE and basic software events is empty, then I can go on and generate the code. I will also show you what happens when I close the RTE editor, I get informed that one additional step is necessary, and that is to run the service needs assistant. It's another kind of wizard in the tool that takes care that the needs for the RTE from the operating system, for instance, is now configured also in the respective modules. So in addition to the two tasks that I have just created, I need a little bit more from the operating system, especially the mechanism here to activate my tasks, so that they meet here the required timing behavior of the events that I've just mapped to the task. So I can also just show you, this is here just another wizard that calculates service needs, and it will perform the calculations. And then also here in the operating system, I have some automatically configured parts, especially here. One of the schedule tables have been just created, and the C overlay icon indicates that that is a calculated configuration and not a manual configuration. That was step 5 of the workflow, which leaves only one last step in the methodology, at least the last step before compiling, and that is the code generation. Specifically generating the code that translates the ECU configuration, which after all is still some kind of XML code, into code which can be compiled. Here on this slide we see an example how this looks like for the CAN interface module. The CAN interface code generator creates a bunch of files, and this is depending on the configuration class of the parameters, because if you go deeper in the AUTOSAR methodology, you will find out that there are 3 different configuration classes: precompile, link time, and post-build time, and therefore this also results in the 3 different bunch of files generated here by the code generator. Typically, the modules consist not purely on generated code, but also on non-generated code, where the actual functionality of the module is then coded. So in this example, we have a bunch of configuration files which will be generated as a result of the ECU configuration, which was done in tresos Studio, and also here some non-generated files that also contain the implementation of that module. And only when we have the generated code available, it will be possible here to compile and finally link these modules to the other ones. So as the last step, I will show you how code generation is triggered in EB tresos and where you can find the generated files. Code generation can be done here by pressing this hammer symbol. It also shows me that code generation here for the currently selected project is performed. And then it goes through the complete list of modules which are part of my project, and it's running the different generators. tresos Studio itself can implement different types of generators. The most used ones are the template-based code generators, where there are template files, and via a macro language, these template files then are filled in after parsing the configuration files. But tresos Studio can also just trigger even external generators. That is also possible, and by using this approach, it's also really easy to integrate third-party modules inside the same GUI. Now I show you where you find the files which I have just generated. So in the output generated folder, there are now more folders where we can look into. One is the include folder. And just taking the same example which I was showing on the slides, the CAN interface, you see here all of these files have been generated which belong to the CAN interface. These are the header files, and in the source folder I will also find the corresponding files for which contain the corresponding elements of the configuration here in C. So, of course, this happens not just for the interface, but for all the basic software modules and also for the RTE. And taking these files, and of course, you need also to add the application itself that makes up the implementation here, for example, of the software components. It needs to be added also, and then you can go on and compile the complete project. Okay, let's have a short look of what I've just presented. So first of all, the AUTOSAR methodology for the Classic platform covers the complete development cycle from the definition of the system, in our case a vehicle, a car, to the generation of the code. And it is divided in two parts. The OEMs typically provide an ECU extract of a system description to the tier 1s, who implement the ECU, and then starting from there, this typical workflow, which I was just demonstrating, includes the following step. First step is always to import a system description. Second step is to complement the system description by the basic software module descriptions, which are also part of the system description, but they are provided by the basic software modules themselves. The third step is to generate the ECU extract, the complete scope of ECU extract, including, for example, here the combination of the port connections and the flat hierarchy of software components. The fourth step was to derive the ECU config from the system description that is possible for the communication stack as well as for the diagnostic stack. Fifth step was then to configure the remaining basic software modules according to the ECU requirements. And once all of this is done and you have consistent and valid configuration of the ECU, then you can start with the code generation and compile your executable.